Hello, my name is Ray Sanchez, and this is the Fluids Lab final project. For this project, we are going to be comparing the velocity at the exit. In this case, the exit is a hole near the bottom of the plastic bottle in order to get the volumetric flow rate. We're going to measure the diameter to get the area and then solve for the velocities to compare them. First, what we're going to start off doing for this project is to fill up the plastic bottle up to the marked line or just close enough to the marked line. After that, we're going to add food coloring to see the water flowing better. We are then going to make our hole where the water will flow out from, which is near the bottom, very carefully. We can see that when the cap is on the bottle, there is no water flowing out. And this might surprise you. You might think that because there is a hole, water will escape from there. But if we remove the cap, you can see that there is now water flowing out from the hole, and it stops again when we put the cap back on. If the hole gets a little larger, as shown, then some water will start flowing out, even when the cap is on. We are now going to measure the volumetric flow rate for the water coming out through the hole by measuring how many milliliters of water is filled in a certain amount of time with the cap on and then with the cap off. Hello guys, this is to continue the Fluids Lab project, and now we're gonna go behind a little bit behind the theory, behind the scenes as to why is it that when the cap is off, the water starts flowing out, and when the cap is on, it doesn't flow out of the hole. So if we go here, into our first schematic, my first picture, we can see these little gray lines all around, right? And what are those little gray lines or these gray arrows? That's just air pressure, right? Air pressure all around acting on the water bottle. Even though we can't see it or feel it, there's always atmospheric pressure all around. So atmospheric pressure is 1 atm or 14.7 psi at sea level, right? So now we go to the second schematic here, and we made the hole, right? So now we go to our third schematic. We've made the hole already, small enough hole, right? And this hole, even though there's a hole there, there's no water coming out. And why? Why? Because again, this atmospheric pressure or this pressure all around is acting on the bottle, and this pressure right here, it's acting on the water, and it doesn't let it come out. But that's when the cap is on, right? When the cap is on, it doesn't let it do that. So when we take the cap off, however, now because we said that there's air pressure, around it acting on the water, on the bottle, this air pressure, the pressure, the air can go inside here and push down the water, which makes it now it's gonna make it flow out, right? It's gonna push down, it's gonna make the water flow through that hole because of the force, right, that the pressure makes, and alongside with the force of gravity, it's strong enough to be greater than the atmospheric pressure here, and the pressure acting there on the hole. So, and then also, what if the hole is larger, gets larger? Well, that's not going to be enough pressure also to keep the water inside, right? Okay guys, just to follow up on why when the cap is off, the water starts flowing, or why is the velocity greater when the cap is off, we can utilize Bernoulli's equation. Bernoulli's equation for steady state and compressible flow along a streamline, it's this equation right here, which is pressure 1 plus rho, which is density, v1 squared, which is the velocity at point 1, over 2, plus rho g, gravity, Z1, which is the height, or the distance from the datum to the point, equals pressure 2 plus rho V2 squared over 2 plus rho GZ2. So we take our datum to be 0.2 here, and here, this is the axis, XY axis, and we can take the height from the second point to the first point to be h. So if it's open here, that means that it is open to the atmospheric pressure. P1 equals P ATM. P2 here in the hole is also open to atmospheric pressure. So P2 is also P ATM. So we write this in terms that we know, P ATM plus. So now our V1 is going to be 0 because that is where the water is right here. The velocity there is 0. Or that's our reservoir, so the velocity there is 0. So now we're going to say rho G Z1, which is the distance from the datum to point 1, is h, plus P ATM again, which is pressure 2. Z2 is 0 because that's where we chose our datum to be, plus rho V2 squared over 2. So we can cancel out both P ATMs from both sides. We're left with rho GH equals rho V2 squared over 2. We can cancel out the rho's on both sides. This is GH turns into GH equals V2 squared over 2. Multiply both sides by 2, and you're left with 2GH equals V2 squared. Take the square root of both sides. The square root of 2GH equals V2. So to calculate the velocity 2 at the exit, where the hole is, you can use this equation, square root of 2GH. And if you've taken a physics course before, you might say, well, this equation looks familiar. Well, that's because maybe you have used it before. So let's take that here is a tree, right? And there's an apple here, and it's just waiting to fall off. What's gonna make it to fall off? Well, it's gravity, right? Conservative force, gravity, or any other force if you apply to it. But in this case, if it falls by itself, well, that's just gravity. And the distance from the apple to the floor is a distance of h. So that means that the apple is actually in free fall. So because there's no non-conservative forces acting in it, just conservative force, which is gravity, we can say that when it's at the top, it has the maximum potential energy that it can use, or that it has stored. And just before it hits the floor or the ground, it's going to have the maximum kinetic energy. And remember, potential energy is mgh. Kinetic energy is 1/2 mv squared. So then if we equal them because of the law of conservation of energy, remember, which is this, the energy is conserved, we can say that our mgh and our kinetic energy and our potential energy, we can equal them to each other, cancel out the m's, and we get gh equals half v squared. And this equation looks familiar, right? Now we solve for v, we get that 2gh square root of 2gh equals v. And that's what we just got right here. And why is that? And why does this equation look familiar? That is because Bernoulli is actually derived from the law of conservation of energy. So what does that mean? That means if we go over here and draw a water droplet, say that water is falling here at the same height of h, that means if it's also in free fall, right? If it falls, when it reaches this height h, the same as the hole, that means that it will have the same velocity v2, right? Or v, which is what we just solved for. So that is why water towers, this is your water tower right here, that is why water towers have to be really tall. They have to have a really big h, because the bigger the h, the bigger the larger the velocity that is going to come out of your hose or out of your faucet. So that's why water towers, for example, have to have a really big height.